Is it better? Can you hear now? Still echoes? Can you hear?
Yes.
Okay, good. The question is about international cooperation in the astrophysics. We do hear from other frontiers about their participation in experiments abroad and vice versa. So how do you see that sort of helping in the astrophysics, and how you approach this? What's the challenges?
So just to give an example, both DESI and LSST are strongly international. DESI spans many countries. So the fibers, for instance, were all put together at Durham University in the UK. France made major contributions. Similarly with the LSST camera, IN2P3 has been very heavily involved. And the telescope itself, of course, will be in Chile. So these projects are already international in dark energy.
The same is certainly true for gravitational waves, both current generation and next generation. There's the European project Einstein Telescope, and there it's actually even for location. So there's an actual science reason that we want international observatories, multiple across the world.
For CMBS4, there's many international collaborators, especially in the science collaboration. And the project is currently working with international partners in developing in-kind contributions. But it's early days for that for CMBS4 still.
Chanda, you've got your hand up.
Yeah, so I think, we can actually look at the snowmass process itself and see that there has already been international collaboration just in the ideas that I talked about. Our facilitators who worked on the solicited white papers for Cosmic Probes Topic 3 included people from India, people from around Europe, people from not just the United States, but also Canada and in North American context. So we have been treating, at least within CF3, we have been treating this like an international process that may be rooted in the US, but certainly draws from ideas and collaborations that are going to be international in scale. I do think that as we continue to develop these collaborations, including thinking about in-kind contributions, and I'm super proud that in the dark matter working group at LSST that we are also quite international, but have room to grow there, that we be conscious of countries and communities that are typically excluded from participating in American science, and that we be particularly active at bringing those communities in ways that are equitable and fair. So I just want to identify that as something that I think should be a priority for us going forward. And again, is very much in line with what NSF and DOE have identified as priorities for enabling science.
Okay, and I think I'm going to take my prerogative as having an opportunity to ask a question. I'd like to know about key enabling technologies that we see driving the progress in the cosmic frontier for the next decade.
So I could, I hope you can hear me. I had one idea to talk about here, which is the exploration of the electromagnetic spectrum with instruments from the infrared to the microwave. So you know that in particle physics, we got a lot of mileage out of detecting single optical photons. It's only recently that the capability to do this has extended into the far infrared. And now, thanks to our friends building quantum computers and so forth, there is even the beginning of a technology to see individual microwave photons. So this capability to see single photons over this enormous energy span, I think, is the key to low threshold detection for light dark matter and also for axions. And so I think that's an emerging theme for sure.
Yeah, so similarly for gravitational wave detectors, there's a number of technologies. One of them is also improving the quantum limit technologies to improve that and push the sensing beyond just the regular shot noise. There is also some R&D going on for ideas like cryogenic interferometry to reduce thermal noise in the mirrors and make them more tolerant to high circulating arm powers and things like that. However, the really big step for the current detector will really come with the new facilities. I mean, it's maybe a little too aggressive to call advanced like a prototype, but it certainly was the first machine that was built for discovery. And now that we know what signals we will go after, we really need to design the machine that can do the most science. So that's sort of the next development step. And that's really where I think the DOE can really make an impact. It's also worth mentioning that the LIGO community really grew out of the high energy physics community back in the 90s. A lot of the experts that built LIGO control systems, etc., came from the high energy community. So there is lots and lots of know-how overlap there.
So maybe I will add a couple words about large scale computing, because these experiments are growing in data pretty dramatically, and it's something that's new to our community. I'm not 100 years old, but my first dark matter experiment, we had a hard drive that we used to copy data from underground at Gran Sasso to the surface. Now the scale of LZ, which is not one of the large experiments, we write 1 petabyte a year, which is a third of Atlas, 5 petabyte total. We have to use a supercomputer to look at the data. We're stressing the boundaries of networking, of storage, of computing. And we're doing a search with a sensitivity of signal to background of 10 to the minus 9, which means we're pushing the boundary of machine learning, even all the most advanced algorithms. So that is pretty new to our community and is going to be crucial to the next generation of observatories, I think.
Yeah, I think it's illegal not to mention machine learning, and machine learning also has lots of applications in astroparticle physics because we receive large amount of signals in our detector. It's very computationally exhausting to reconstruct every single event. For example, as you receive millions of events every single year. So machine learning has been greatly help with the reconstruction of these events and study the purity of individual and help us to reconstruct this information.
Yeah, for DESI, a key enabling technology has been new fiber positioners, robotic positioners that allow us to target 5,000 galaxies at a time, collect their spectra simultaneously, and in less than a minute move to another set. And so in the course of a year, we obtain more than 10 million redshifts. And this is continues to be a key enabling technology. If we can make these smaller, we can look at not 5,000 at a time, but 20,000 objects at a time or more, and survey many types of objects, look at dark matter and dark energy at the same time with future projects.
In the CMB, the big breakthrough has been the development of monolithic detector wafers with many hundreds and even thousands of detectors on a wafer, compared to just 10 or 20 years ago where we were building them by hand. And that's what's enabling CMBS4. And certainly with that comes an enormous increase in the data throughput. So the data and simulations especially is really a big driver.
And maybe the other side of that question is, where do we see the key synergies between theory and simulation with Cosmic Frontier experiments?
It's on. Okay. Yeah, I mean, there's tremendous synergy on within cosmology and the theory frontier, within the cosmic frontier, but specifically within cosmology and the theory frontier in a number of areas. I mean, we draw on models that, we talk to string theorists to get input on what types of models we can write down that can generate the observable universe. We engage with particle physicists, dark matter people building models of beyond the standard model physics, what signatures we should be looking for. But particularly, we actually have, there's so much fantastic work has been done that we now have, we have predictions for observables that we don't yet have, that we need theoretical work to be able to realize those measurements with the next experiment. So also theoretical work and simulations to model the data itself and the observations.
from the, sorry, didn't see, do you want to go? From the point of view of direct matter detection, we saw earlier a graph with hundreds order of magnitude by hundreds order of magnitude. I don't know how to look for any of those. I know how to look for a WIMP because it's kind of similar to a neutrino, but that's about it. So I need the theorists to tell me what these particles look like and how you look for them. And then, I can build it, not by myself, but we can build the instrument, but we don't know how to look for those exotic models of dark matter.
So I think for multi-messenger studies, the beauty is you can use multiple messengers and cross wavelengths to solve the same problem. And that enables the study to compare the same theoretical model, which predict multiple signatures in different messengers and wavelengths to be compared with data simultaneously. But to achieve those kind of studies, I think some infrastructures that enable combined fit cross different messengers and sort out the systematic and statistical errors across different facilities is quite important. So I think those are something that need major efforts to promote the next generation studies of multi-messenger particle astrophysics or particle physics.
Chanda?
Yeah, I want to start by actually pointing people to the recordings of the Tuesday plenaries if you weren't able to attend, particularly to Tracy Slatier's talk and also Risa Wexler's talk, where I think that we're seeing a lot of really great examples where there are important synergies between theory, observation, and experiment and simulation, where they are driving each other in better directions and more powerful directions. I think the example that is probably pretty low-hanging fruit at this point is ultralight axions and more broadly scalar dark matter models, where there has been an explosion of interest, particularly over the last few years, and huge continuing interest, I think, going into the next decade, where we see that string theorists are driving conversation in astrophysics. And simulators are going back to the string theorists and saying, well, can I put this property in? And so there's a very clear dynamical relationship there, where then the simulators and observers are then in conversation about how, for example, Vera C. Rubin Observatory is going to pursue that. We're now also thinking about these beautiful new images that we're getting from JWST and dreaming about what we're going to get from Nancy G. Roman Observatory. So I think that there is a powerful dynamical relationship there, not just between theory and observation in the cosmic regime, but also simulations are really key. And I think that in a lot of ways, the sky is the limit with simulations. We are limited with simulations only in our ability to support them through having funding sources to ensure that we can actually move forward and do all of the work that we want to do and process different universe models. And so in order to not have to make hard decisions about that, we have to be able to support particularly young people who are interested in taking things in that direction. And I just want to emphasize, just to go back to you, Dave's question earlier, that when we're talking about training our early career researchers, that developing those skills with theory, simulation, and data together actually position them very well for whatever jobs that they may decide to do in future. And so emphasizing those synergies is valuable for us as a community, not just in terms of our own academic scientific work, but also ensuring that people have the right training to go out into the workforce wherever they decide to take their skill set next.
We can sneak in one more question if we've got one. All right, well, do we have one on Zoom? I'm not seeing one, even though people are pointing. All right, well, let's thank the panel for a really exciting time.
So folks, I could do with a favor. I noticed there's a bunch of like empty coffee cups and other things just floating around. If there's one near you and you could take it out, that would be great. And the other thing is their physics slam is here next. So if you don't want to stay for that,